I would like to invite on stage please thank you ค่ะขอเสียงปรบมือให้กับวิทยากรของเราด้วยนะคะ
this front, right? Okay. Okay. So I'm Daniel Chen. So I'm happy to be there to introduce about the generative opportunity and challenge of the generative AI-driven PCB. Okay. And really, I think this seminar is being sponsored by Wellink and also Tangent, and also 10C. And by the way, I'm also supported by the Thai PCA and also the CPCA. Okay, let's move on. So this is my picture. And basically, I was the IBM Global PCB Global Council Chairman for sourcing of PCB for more than 300 million every year from the 2003 all the way to 2014. And I'm really helping IBM to developing the high-end, super high-end computer solution, PNC, and also about the peripheral. And also I'm the Asian guy really involving about the flip chip BGA development in around 15 years ago. So pretty long time with the flip chip BGA technology. And also I am also the technical consultant for the Hong Kong printed circuit board and also CPCA and also Tangent and also the 10C, okay? And by the way, I can tell you that I think basically Tangent is a company producing a lot of high-end equipment, including the laser joule machine that can help in doing the AI generative PCB. And also for 10C, they also doing a lot of electroless and electrolytic plating solution for the high-end server. I can tell you like a lot of SSC and also a lot of high-end PCB guy really doing everything, okay? So we as a professional team here, I can tell you that I myself is with global footprint because I'm IBM. So at that time, I'm working with the US guy like the TTM, EI, and also I'm working with the Japanese, the Hitachi, okay, Kanagawa, Fujitsu, and also I'm working with the other guy like the in Taiwan, Gold Circuit, and also like the Woos and so on, right? So to me, as a company, as a team here, I'm going to helping those guys interested in the generative AI technology, which is the front-end technology of the printed circuit board or the IC carrier. I will tell you later. And to me, I have a lot of pattern technology things, and we are providing the professional solution as of how to manufacture the IC carrier about the AI generative interconnect. And also, we are concentrated on the innovative technology, particularly the Tangent. We have the latest technology of the carbon dioxide laser joule machine, which is equivalent to Mitsubishi, all right? We also have the laser direct imaging technology. This is equivalent to screen and also even better. Okay, I will show you later the data and so on. And also, I've been working with the 10C about the electrolytic solution and also the electrolytic technology on plating the chemical, particularly on the microwire and particularly on the high aspect ratio pH to fulfill the server requirement, okay? Okay, this is the machine. I think we are having like the CO2 using the liquid carbon dioxide instead of the gaseous carbon dioxide, which is more stable. That can drill up to down to 60 micron diameter, and also the LDI and DI down to around 10 micron technology. And also we have also high reliability of the electrolysis and electrolytic solution, helping to produce the AI require PCB technology. Later on, I will show you why this is important, okay? So we are selling to globally, US, Japan, and Thailand, and so on. All right, go to what is generative AI technology. And to me, when I was in IBM, where I have been talking about AI. So AI, by the way, we have been using a lot of AI in CNC drawing, by the way, machine learning. Okay, in IBM, we are using and developing so-called analog computing, also AI, and try to simulate the AI technology with reference to the monkey brain neuron internet connect system. All right, so, and now I can tell you, suddenly in these 2 to 3 years, the generative AI become very popular. A lot of people may not aware what's happening about the generative AI. What is this? And before, we are using Java, C++, etc., using the programmer, using the analysts to teach the machine to run exactly what they want. 1 plus 2 equal to 3. That kind of thing. Exact science. However, the limitation of this kind of artificial intelligence is limited by the intelligence of the programmer or the analyst. And now, suddenly, we go into another school of thought, like a human being. It is in a scenario, we are not teaching the computer to execute the artificial intelligence. Rather what? We input a lot of information inside with a matrix mathematical calculation or matrix logic, and let the computer to understand logically and store the information into a logical manner. In a scenario, they get larger and larger data, they get more and more solution with the classification. Once you ask them similar logic, they will give you the solution to you with reference to the logic. So the scenario is totally different. Before is we teach the computer to do whatever we like. We call it machine learning, artificial intelligence. Now we call it deep learning generative artificial intelligence. All right? So in this scenario, I can tell you, is fully deep learning is more kind of structural before. Now it's non-structural can be, number one. Number two, can be cognitive capability. That means he can think, he can learn, and classify, and can be very big database in that scenario, and can be very intelligent. And with data analytics, very important. I'm not sure you tried before. Using the so-called LLM, language large model. Now he can talk to you like the ChatGPT. He can understand human being. You can use a normal language to communicate with the computer. Before, you have to using Java, you have to using C++ language that you may not familiar with. Now you're using common language to talk with the computer, right? He can understand. So this is the differences. So in that kind of scenario, using the big data analytics, the human being can be very easy communicate with the computer and very close to the real world and give you more accurate data, like the translation. And today I'm using a lot of general computer for me to translate and even doing the simultaneous interpretation. Or even in the future, people talking about is the robot can understand me and helping me to do a job, right? So this is the future, right? And this is the future. Okay, so in that scenario, you can understand, before the programming language, the data is very limited. Now, because of what? All the large data, the data is very big, number one. And also the analytics requiring to be very fast to go to search and translate or decode the concern. So in that scenario, there's a strong demand on the hardware in terms of storage, in terms of processing power. All right? So this is basically the differences. This is also good news for PCB or IC carrier, I tell you later, because they require big storage. They require very fast memory. They require very fast GPU, okay? So that kind of scenario, all right? So you can say AI is something like an NPU, neural processing unit, okay? So in a GPU like the NVIDIA, they have many so-called NPU to helping you to process in parallel mode. So this is what they're doing. So in terms of the potential business, so whenever we invest in anything about the AI-generated computer, the very important stuff is how much the business can be generated. I can tell you today, the demand of the server increased by 200% more this year. So the demand of server and also the SLN card will be a big business to the whole industry. So anybody can capture the generative AI, he will get a big profit. Like the people doing at NVIDIA. Okay, like you can see the public report, like something like a lot of Taiwanese, they got a huge profit because they have ability to do the 6 plus n plus 2, plus 6 plus 2 plus 6, and consistently. So they can enjoy a very good price and very good margin, all right? So this kind of scenario, I can tell you, according to the statistic, 2005 server demand up 203% at 121 billion, something like that. So the origin of the generative computing or generative AI is basically from 3 people. A lot of people know him very well. Jason Wang, the CEO of the NVIDIA. And he's the guy really creating the Cooper, designing the acceleration card H1000 or B2000. In that scenario, there can be the latest one called Blackwell. They can up to 1 trillion parameter scalable AI model. And that can be running very fast, okay? Up to 20 petaflops. Petaflop means the floating operation points per second. So this is guy earn a lot of money. And now they're becoming the richest people in the world, right? Very, very, very rich. And he become a very famous man. However, at the back end, there's 2 guys very important. One guy is called the generative AI Godfather. And he is the guy creating the Jeffrey Hinton. He's the guy creating the neural mathematics, the matrix. And he created mathematics. And this lady called generative AI godmother. Okay, this is from Hunan, it's Chinese. All right, Professor Fei Fei Li at the Harvard University. He's the guy using the Jeffrey model to create the image lab. She's the lady, the first one, using deep learning to understand imaging process with the large model. And then creating, you just call, I like a red dog, he will give you a red dog. I like a dancing dog, he will give you a dancing dog. That kind of scenario, okay? So this is 3 people really creating and shaping the beginning of the generative AI. Okay, go in the hardware, this is software. So this is the background. So why the generative AI is so important to PCB? It is because they're requiring high demanding of storage and processing speeds. So in that scenario, like this one, I'm using an example of the NVIDIA Blackwell IC packaging system. You can see that there's 2 die. At the 2 die, there's 4 memory, we call it HBM, high memory, high bandwidth memory. And they're connected with what? What they're doing today is, with that very complex substrate, around 20 layer, super low loss material, very low profile copper foil, and 7 to 8 kind of stack up, that means the additive layer or any layer, with the live spacing talking about 10 to 12 micron. And then today, in Taiwan, like the Unimicron, TSMC can do it. And then in between, they call it interposer. It is basically why interposer? It's a silicon. And for the silicon, they can communicate between chips with wafer. And the wafer talking about, the DF talking about 0.0002 or 3. Then in scenario, they can be very fast, can communicate with the memory and the GPU. So in that scenario, the chip is super fast, okay, super fast. So this is the substrate. HBM, SoC, HBM, interposer, and then substrate. So this is currently, this technology is happening, all right? Okay, going into more detail. So this is what today. So I'm really happy want to show you that kind of information and let everybody open up the technology and let you understand. The circuit board, I'm talking about later. The packaging substrate, as I mentioned, is very complex one. And you know how much per substrate per square meter? 100 million, a million to 2 million per square meter. That kind of range, I can tell you. Very expensive. The line we're talking about is 15 micron to 12 micron things with very complex, we call it HDI, interconnect, and with the interposer. The interposer basically are double-sided things with the TSV, okay, transistor weir, with the copper pillar. And then on top, there's a HBM, high bandwidth memory. They will talking to each other and store a lot of information and can be very easy transferred through the interposer to the logic chips here. All right? So you can see this is the beginning of the capacity of the IC packaging. All right? So this is a key parameter. I will not go talk about it. If we have time, we can talk through individual cases, professional services, TSV, GPU, HBM tagging, and GPU chips on chip in the future, etc. Right? And in IBM, I was the guy involving the flip chip technology. At that time, our maximum size of the substrate is 50 mm times 50 mm. The reason behind is warpage. I cannot overcome. And my boss wanted me to produce a 100 mm times 100 mm. I failed around 10 years ago. Not easy. Because of warpage, we create the very poor interconnect of the die, okay? Because die is very fat. Okay, so this is the future technology everybody should be aware of. All right, so I can tell you, this is the AMD latest design graphic chip. And this is really connect with, you can see, very complex, 2.5D, 3D, and 3.5D. They can be SoC on SoC and then on interposer with all the interposer things. So it's very complicated in the future, all right? So this is what can be offered by TSMC today, all right? Wire bonding, and then they call it the chips on wafer on substrate things and so on. So this is what the Intel. The Intel is basically, mainly they have an embedded technology. They can be embedded a silicon. They can be using to communicate between the SoC. So this is what the Intel doing. And however, you can see that here, the power consumption is huge. 700, 800, even maybe in the future, 1 kilowatt. Very huge power consumption. So this is the problem in the future. A lot of people saying that in the future, who can generate sufficient electricity to support the AI? Here with the country, they can be doing everything. So the power consumption for the AI will be huge, right? So this is the interconnect system for GPU, CPU payment. So this scenario has been doing a lot by like a lot of company. I don't want to say that company, but in public. All right? So a lot of big company, I can tell you. And they earn a lot of money. And this is what Jason will show the guy back well. And I can tell you, you can see that chip is with an angle. Why? It's because the offset, offset about the fiber bundle decay differences. So that's why they need to turn around the about chips to offset the concern, right? So this is the bedwell, and the configuration can be varied. But in general, I got the information from public. It is for the isolation count, and it is a 6 plus n plus 1, but x plus n plus 6. That means this is a 6 layer, any layer. Wow, 6 layer, any layer is really very tough. I can tell you, a lot of people can do 4 to 5. Or I talked to some of the guy here in Thailand, the biggest guy, the best guy, can do around 4. And now it's doing 6. And next, I can share with you, this is the optical module. I want to go to the detail. And I can tell you the optical module guy, the biggest guy, I can tell you, these are 3-dimensional things. One is the modulation, how to decode and uncode the signal with the carrier signal. The other is the number of channel, and then the signal per channel. And today, I can share with you, in terms of optical module, for the 1.6T, it's being pushed very hard by NVIDIA. Because the server to server, if you know about the mainframe, you see at the back end, before IBM, there's a so-called a lot of yellow wire. They're connected with the cable. Now it's connected by optical fiber. Everything connected by optical fiber. And the optical fiber needs to be connected by the optical puck, optical module, to translate the electrical signal to optical signal, all the way to the optical fiber. And now, before, I think the mainstream today for the optical module is around 800G is the standard, or maybe 400G. Now, push very hard to 1.6T. And the signal transmission is 8 channel, more popular. Within there's 8 lights all the way with different angle to pass through, 8 channel, for which channel transmitting 200 gig per second. This is a very fast one. All right? So in this scenario, I can share with you, if that kind of small size scenario, the optical module has been going into very miniaturized in terms of light with 30 micron. Number 1. 6 plus n plus 6. Number 2. Super low loss material with a DF talking about 0.0015. And then the last one, using the HVLP to avoid the skin effect. And that kind of things. Very complex PCB. And I can tell you, you want to get a fortune, you get a good technology. For the 400 gig, today's selling price, around 300 RMB. For 800 gig, how much? 1,006. For 1.6 gig, how much? 4,000 to 5,000. Huge profit if you can overcome the technology. The same for optical module PCB, I can tell you. If you can overcome this kind of stuff, per piece of PCB today is $100 per piece, optical module. I'm not cheating. I have a demand for you. You can produce it. Very hot. And the market is pushing to 1.6 to 3.2T. Very, very hot. And also, I can tell you, if you can produce 6 plus 2 plus 6 isolation count, demanding a lot of capacity. The current supplier cannot fulfill the requirement, okay? So this is the scenario I can tell you, okay? And it's really likely to go to 7 level. And now the designer is talking about 7 plus 2 plus 2, 7. So this is something very interesting, all right? So I'm more than welcome. If anybody want to talk to me about the concern, I'm very happy. Because I'm very, very keen to develop the technology with our partner as to how to catch up the concern, right? So this is something very interesting. So, as I mentioned, as a conclusion, I will leading the team to helping to provide the professional services together with the Tangent and 10C and others to give you a competitive application engineering and optical solution to meet and exceed the latest PCB engineering challenges, particularly on any layer, talking about 4, 6, 5 any layer, step up. Talking about how to manufacture a super low loss material with HVLP. I'm interested in helping those guys to go down to M sub, to go to 25 to 30 micron, and even with the AP, to go down to 50 micron to 12 micron things. I've been running through that kind of stuff before because I'm sourcing before with the Japanese EPDN, etc. Right? So that will be very interesting. I'm really looking forward. If any people interested in, I'm more than happy to helping do that kind of scenario. So now I go to more the background, theoretical. I would like to quick. I will be very quick about the concern. So for IBM classification, okay, every interconnect, we have a classification. Wafer level, we call it interconnect 0. And then IC packaging, we call it level 1. And the PCB, we call it level 2. And basically, they all interconnect. The differences is the substrate. Level 0 is the silicon. And the organic substrate is organic. Now we go to glass. Later on, I'm sure I got glass. And also, go to PCB, is more epoxy and also glass fiber. And by the way, I'm going to show you, very soon, we are going to next year, Intel and AMD is going to push glass substrate. The reason behind the glass substrate is the glass providing a DF down to 0.0002 to 3. They will be enhancing the interconnect transmission, number 1. Number 2, the glass can be helping the rigidity that can be expand the width of the carrier can be up to down 100 mm. They will accommodate more the chiplet, memory, GPU, etc., etc. So this is the 2 reasons behind Intel, AMD, and NVIDIA is going very hard to go into the glass. So let's see, okay? Okay, so this is something fundamental. So we go with the, at that time when I was IBM, I'm doing some kind of the evaluation about the HVLP, etc., etc., and with different combination. And we found that the copper foil, the resin system, the glass system really affecting the insertion loss or transmission loss. Okay, definitely there's a lot of detail. I'm not going to that one. I'm just telling you that the parasitic PCB inductant, resistant, capacitant can create a lot of noise problem in terms of signal integration and power attenuation. Okay, we lower. So in that scenario, we found that the low decay class and HVLP, the copper foil, the etc. And also, I can tell you, the glass here versus steel with different decay, they will affecting the signal integrity, right? So if you go to very precise, I can tell you, there will be have significant effect. At that time, we are using spread glass and so on to resolving that problem. And so this is so-called the I share with you about the fundamental of the parasitic PCB electrical characteristic in terms of conductance, resistance, and so on. I'm going to go into in detail. And you can see that, like IBM and so on, they will design that kind of scenario. Two lines run in parallel because they want to differentiate and canceling the noise so that in up the serial integrity. And also, they will just rotate the concerned BGA to really to offset the gas bundle pattern differential of DF and DK and so on, right? So this is something I can tell you, a lot of things can be done in terms of product engineering and so on. And I will share you about the potential impact in addition to the IC carrier, in addition to the optical module, in addition to etc. things. There's something happening. I can tell you in terms of things, one will be very huge demand is the AI PC. I talked to one of the top guy in PC. He told me that the number layer, because of the AI enabled, they were going to from 6 to 8 layer up to 8 to 12 layer. And then some product with 1 plus or 2 plus or even 3 plus any layer. All right? So that kind of stuff will be demand huge. And also the handphone interconnect will be also up in layer, up in signal integrity, using different resin system, using different copper foil, all right? And definitely, the industry of traffic with the AI enabled will go the same thing. They mean becoming faster, higher bandwidth, and so on. So there will be a lot of demand of the HDI, any layer, a lot of channel, and so on. So in addition to concern the automobile things and also the AI PC, in addition to the base communication, the base station, everything will change. So in that scenario, if you are the PCB guy, you will be lucky because you get a lot of higher value for you with the demand. So that will be very interesting. In addition to here, the big data center today is booming, right? So this is something about the fundamental of the serial integrity. I will not go into detail. I can tell you with IBM at that time, we are using the mainboard as a reference. We found that the thickness of copper is very important because of the impedance. All right, so we try to using as thick the copper as possible to reduce the signal delay, number one. Number two, we are using the line width minimum to be 75 micron because of the resistance and impedance, not affecting the serial integrity. However, with different kind of configuration, like the handset, shorter line width, and then with that kind of sum, you can have smaller line width. However, I can share with you, the copper thickness and also the line width has significant role in terms of signal integrity. All right? So this material very fundamental. The material with the electronic filler affecting the DF, DK, this is very important. Now, talking about EMC, 8-line series is very critical. And also, they're using the foil, very critical. And now, today, the best material I heard is EMC and Doosan, Korea guy, okay? And this, I'm not going to the detail about the impedance control and so on. But what I'm sharing you, I have experience. You meet the impedance does not mean you can have the high frequency, high bandwidth PCB functional okay. I can tell you. All right? I can tell you. Because the polar machine only run at less than 10 gigahertz. All right? So I just telling you, just for your control only. But if you want to be functional okay, but there are a lot of high frequency and so on, you need to managing a lot of things. Today, I'm not going to go into detail. A lot of detail need to be going into to assure the serial integrity versus the high frequency is totally not just only controlling the impedance. And very important, why go into LDI? Because of the stopless requirement. Before, I think traditionally, Intel and IBM, they were requiring the battery to remove the antenna effect That means the excessive through hole, because that will create antenna effect to emitting the signal out, creating a power attenuation problem. Now we go into a step via that will reduce the concern, become a stopless. All right? So today, the latest GPU and also the IC substrate carrier, they all stopless. So no need for battery, but except traditional Intel. Definitely, I will not go into detail. This is not, I can share with you, I can teach you about how to measuring the signal integrity in a laboratory sense. You need a very good VNA, vector level analyzer things. You need to build a test vehicle. You need to do a lot of things. You need to follow a model. You need to, like the IBM, we're using the SPP, short pulse propagation, with the Fourier transform mathematical calculation to find out the very accurate relative DKDF with reference to certain percentage of the resin content, that kind of stuff. So I will not go into that detail, right? So this is what I'm doing before in my last 10 to 20 years, as of how to managing an exact science of signal integrity, which is scenario, low frequency, you don't need to worry about it. You go to high frequency, you need to have a very good system that will be your differentiated assets in serving your customer, I can tell you. So this is very critical. And I'm not going to do detail about how to do a very accurate AOI, smaller pairs, control the lamination cycle, and do a lot of good cooling system. And the live and spacing you need to be controlled, to exercise, using a vacuum lamination, etc., etc. I will not go into detail. And definitely you need a good AOI, LDI, that kind of scenario. So I will not go into detail. And then definitely you can have a good plating. This is a vertical one before using a pulse plating for the back panel, bar panel. Now today we're using the VCP. Now I'm working with a guy going to be a VCDP things, vertical, continuous smear and plating system that is touchless, etc., etc. So a lot of technology. This is what my modeling about HDR reliability. And then I can tell you, you need to move in that direction to increase the adhesion of the microwire. And then you have to push that direction to remove the potential of the microwire to be separated. And then you can create the final result of the concern, how much the force will create the demarcation or separation of the interconnect. I can tell you today, the generative AI, the major challenge is when you go to 6 or 7 or 5, the interconnect pillar between the microwire, the separation, demarcation is the major problem. That will affecting the interconnect. So this is the really very key, and this is my model, I can tell you. No one in the world have that one. This is my model about the concern, okay? And this is interconnect, I don't want to talk about it. And again, very important. Whenever you do anything about signal integrity, you need to create a meaningful, we call it test vehicle. So this is test vehicle, I can tell you, very important, very useful. All the isolation tests, all the stress tests, signal integrity, registration, to really understand about the interconnect and make sure you don't have a problem before you go into production. It is a TV, try to understand how good your capability and how good you can control your manufacturing process. Through that TV, you can improve key parameter, and also you can helping to show your customer what my data is, then prove myself can do the job for you successfully. So this is something I always stress, the TV is very important. Not just direct go with the PCB. You have to use the TV to qualify your process by technology. So this is always before I'm being taught by my engineer in IBM. We have to be step by step qualification of the technology before you go to part number qualification. If you want to do a good PCB manufacturing, this is the fundamental, okay? So that's all I can tell you. So I can tell you, If you want to talk to me about technology things, I can talk 2 to 3 hours to you, no problem, for particular subject like the CNC drill, like the plating, like the signal equity, and so on. So I'm more than welcome. Anybody interested in, particularly in Thailand, when I was in China beginning, I started to helping those don't understand PCB to start the PCB engineering learning. And today a lot of leaders. So I want to do something here in Thailand to helping a lot of young engineers to understand about engineering of the printed circuit board. And then I'd like to work with the university to identify the research project. All right, so I'm helping in China some of the postdoc students to doing the postdoc study about the research subject. So I'm more than welcome. So we can have people from China and people from Thailand work together on the research subject on the particular high-end stuff. I'm more than welcome. So that's why I'm working with the Thai PC very eagerly, and then I'm organized a fundamental training course for the Thai young engineer. So hopefully, I will be having your support to attend the courses. Okay, don't waste the course. I can tell you, I'm very seldom to organize that kind of course. All right, with my 30-year or 40-year kind of experience in PCB engineering. All right, so thank you so much. I'm sincerely looking forward to your business opportunity. And I'm more than welcome to share what I know because I'm 65. I'm really willing to share what I learned from and transfer that knowledge to the next generation to make an even better PCB for the world. Thank you very much.
Thank you very much Mr. Danielson ค่ะเอาละค่ะในช่วงนี้นะคะก็ถือได้ว่าเสร็จสิ้นสำหรับเซสชันนี้แล้ว